Hi, welcome to the world of electricity. Electricity has an important place in the modern society. It is a easily controllable, and convenient form of energy used for variety of uses in home, hospitals, schools, industries, and so on. When we want to learn about electricity, first we should know what is meant by a circuit. So let's learn what is a circuit. A circuit is a continuous and closed path of an electric current. Here, a simplest circuit is presented. A battery whose positive side is connected to a switch. The switch is a open contact, normally open contact. Now it is not connected, and that is connected to the bulb. The other side of the bulb is connected to the negative of the battery. When the switch is pressed, this makes the contact and the circuit is closed. Now we say there is continuous and closed path of an electric current. So the current from the battery flows through this closed path. It is a continuous path and closed path, and this is called a circuit. A circuit can be as simple as this. It can be very complex, consisting of many integrated chips, switches, resistors, capacitors, and so on. Now, when the switch makes contact, the circuit is closed and current flows through the circuit, the bulb glows. When the switch is off, this connection breaks the circuit. It's no more continuous, so the circuit will not work, the bulb will not glow. This is a circuit diagram using the symbols. We will revisit this slide and learn more about these circuit at a later point of time.
That we have a copper wire that's filled with copper atoms. Copper is one of those elements that has only one electron in its outermost shell, which means that with only a little energy, that electron can be easily ejected. If we push a free electron into the copper wire, it will eventually find a new atom to latch onto. The negative charge of that electron will eject another electron from the outer shell, which will then move on to the next atom, and so on and so on. This chain of moving electrons creates a flow known as electric current. Some elements, like copper, aluminum, and gold, can move electrons easily and are known as conductors. We can look at moving charges in another way. Let's say that this tube is a conductive wire and the steel balls are negative electric charges, electrons in this case. We might think that one charged particle needs to move completely through the conductor to create a flow, but that's not actually the case. As we push a ball in one end, the force causes all the balls to move and one pops out the other end. As you can see, one electron, even if it doesn't move very far, can force all the other electrons to move, creating a flow. What we just showed was electric current, which is a flow of electric charge. In most circuits, this is accomplished by moving electrons. The unit for measuring current is the ampere, which is often abbreviated as amps and written with a capital A. 1 ampere is defined as 1 coulomb of charge moving past a point per second. Let's look at a cross-section of wire carrying an electric current. If it takes 3 seconds for 6 coulombs of charge to move through that cross-section, then we say that 2 amps are moving through that wire. Unfortunately, electric current doesn't just magically flow through wires. It needs a little help. If left alone, the electrons in a wire won't move. We need to give them a little push. To do that, we'll use a voltage source like a battery. In a battery, there is a buildup of negative charge on one side in the form of excess electrons. The other side has a buildup of positive charge, an absence of electrons in this case. The charges want to balance out, but the only way to do that is for the excess electrons to flow around the battery through a conductor that we provide. If we connect a piece of wire to the negative terminal, the electrons will push against the electrons in the wire. However, Air is an insulator as its molecules do not have very mobile electrons and it won't readily accept the free electrons. To show this, we'll put a piece of tape at the end of the tube. Now, the electrons at the end of the wire have nowhere to go. Even if we push against the electrons in the wire, they still won't budge. To fix this, we need to connect the other end of the wire to a place where the electrons want to go, and the positive end of the battery will happily accept the electrons. In fact, don't try this with a real battery. There is nothing slowing down or restricting the flow of electrons, which results in tremendous amounts of energy being transformed into heat in the wire, and this could easily melt the wire insulation or start a fire. This is known as a closed circuit, as it creates a loop from one side of the energy source to the other. If we break the wire or remove it from one of the terminals, then the electrons will stop flowing. This is known as an open circuit. We've been talking about electron flow in a circuit and showing how electrons move from the negative terminal to the positive terminal. However, in electronics, we usually assign current as flowing from positive to negative, or from higher potential to lower potential. This is known as conventional current. In the mid-1700s, Benjamin Franklin theorized that positively charged objects had an excess of what he called electric fluid, and that negatively charged objects had a deficit of this fluid. Franklin noted that this fluid had a tendency to flow from positive to negative to distribute itself more evenly. It wasn't until the end of the 19th century that English physicist J.J. Thomson discovered the existence of the electron. Even though we now know that it is electrons that move inside of most circuits from low to high potential, the convention of current moving from high to low potential stuck. As a result, most current measurements are given as conventional current, which is the movement of positive charge in a circuit, and is represented by the capital letter I. Don't worry, the math still works out as long as we stick with either electron flow or conventional current. And since most electronics textbooks use conventional...
Wow, so much of stuff so fast, isn't it? So let's try to learn a bit slower. What is electric current? Electric current is the continuous flow of electrons in the electric circuit. Okay, so if you have a circuit, if the electrons flow continuously from one side to the other side, you call this as electric current. In metallic wires, I repeat, in metallic wires, when an electric potential difference is applied across the metallic wire, for example, this is the metallic wire, a potential difference is given, higher potential and lower potential using a battery, then the loosely attached free electron starts moving towards the positive terminal. The free electrons in the conductor is, of course, it is negatively charged electrons, and here it's a positively charged particle. It's a positively charged positive side of the battery. This is positive, and here it is negative. So opposite signs attracts each other. These electrons are attracted by this positive charge and they flow towards the positive terminal. The flow of current in the wire is from negative terminal to the positive terminal through the external circuit. Why we stressed metallic wire in the previous slide? How about plastic, wood, and many other stuff that's available? That's a question to be answered. To understand the difference between the metallic wire and other materials, we need to have some understanding about the conduction band and valence band. Conduction band is responsible for the conduction of electricity, electric current. If you take the structure of the atom, you have the nucleus represented by red and blue color circles. The one color representing neutrons, other color representing protons. So what's inside here is the nucleus. The yellow color circles represent the electrons and they rotate the atom nucleus in the orbit. Okay, so they're all completely filled orbits. Orbit 1 completely filled, orbit 2 completely filled, you see. So orbit 3, there are only 2 electrons, and the outermost the layer the orbit in which only there are fewer electrons, and those electrons are called valence electron. Okay, it's not properly filled. Now, still they are. It's also this is a valence electron. Okay, now that is part of the orbit in the atomic structure of the metals. Now, when we give the potential difference, what happens? These electrons comes out of this orbit and go to the, because of that potential difference, it goes to the conduction band, and this happens seamlessly because there is no much gap between the valence band and the conduction band in metals. So when you give potential difference, you see the red color rectangles representing the valence band, and blue one is representing the conduction band. In certain materials, the conduction band and valence band, they overlap. Such materials are called metals or conductors. Okay, uh, the right term is conductor. Metal is one of the examples of the conductor. So now, here what happens, those free electrons, when potential difference is applied, starts moving towards the positively charged terminal, thus thus establishing the current through the circuit. Okay, so in conductor or in metal, this is what is happens, and it is quite natural. This is what is our subject matter. So we took metal as an example of conductor and discussed our issues. How about plastic? How about wood? In plastic, wood, mica, and few other materials, you find that the conduction band and valence band are far away. The band gap between these two bands is very high. So because of that, it is very difficult to push the electrons in the valence band to a conduction band, and so they rarely conduct electricity. In fact, it doesn't conduct electricity. So such material we give a name as insulator. Whenever the valence band and conduction band are overlapping, it is able to conduct electricity. So such material we give a name as conductor. On one end you have conductor, on the other end you have an insulator. There are some materials which doesn't form part of some material which does not belong to the conductor category or the insulator category. Okay, those are called semiconductors. Okay, there is a gap between the valence band and the conduction band in such materials. By adding some small impurities to that material, it's possible to, you know, have some electrons or holes in the conduction band, thus establishing the flow of charged particles. I mean, helping to, do the current. Flow of current is possible by adding some impurities and other items, and the band gap is too small. Such materials we give a name as semiconductors. So basically, we have conductor, we have semiconductor, and insulator. In our subject, right now, we are more interested in conductor. Okay, that's why we have been talking about metallic wire like that in the example here. So now you revisit that slide. In metallic wires, when the potential difference is given, then the current flows from negatively charged terminal of the battery through the wire. It goes to the positively charged terminal of the battery. Okay, so from negative terminal to positive terminal is the flow of electron, and so that's the direction of current. But conventionally, people have been believing that the flow takes place from higher potential to a lower potential. Flow is a natural phenomena. For example, heat flows from high temperature to low temperature. Water, for example, or any liquid for that matter, liquid flows from high pressure to low pressure region. Flow of current from high potential to low potential. So people believed in this flow idea, and they thought that the current is flowing from positive terminal to negative terminal, from positive terminal to negative terminal, the electric current was flowing. That's what their thought process. So in those days, when electrons were not known, the electricity was found. So those days, people thought there is a positive charged particle that is flowing from positive terminal to negative terminal, and they thought, they have decided that is the direction of flow of current. Even today, we follow that same direction of flow of positively charged particle from positive terminal to negative terminal. Just now we have learned here the electrons move from negative terminal to positive terminal because the electrons are the ones which is flowing, that we call it as current. The actual flow of electric charge is from negative terminal to positive terminal. But the sign convention even today for current is from positive terminal to negative terminal. Now we are giving the explanation why the current direction is from positive to negative. That's because of this flow idea people had, the strong belief before invention of this electron, and they thought there is a positive terminal here. Even today this analogy can be used for us to understand there is a positively charged particle here, a positively charged terminal here of the battery. This is a conductor, for example metal. The blue color circles represents electrons, okay, free electrons. When this positive terminal is connected here, this will pull, attract, because this is negatively charged particle, this is positively charged terminal, so opposite charges attract, so that comes towards the positive terminal. Here there were one negatively charged particle, now it has moved somewhere else, that means there is a vacancy. The other name for vacancy is a hole. There were some negatively charged item, now that negativity is not there. Relatively looking at it with respect to the earlier state, now we are more positively charged. That place is positively charged. It's something like, yesterday I had a loan of 1,000 rupees, today I have repaid, so I feel more positive today, because yesterday I had to pay 1,000 rupees loan, I was negatively charged, but today I have repaid the loan. With respect to that, I feel very positive. As of now, in my packet, there is nothing. In fact, there is no packet in my shirt today. But I feel very positive because compared to yesterday's state, it is relative. Compared to yesterday's state, today I feel very positive. Even though I don't have single rupee money, I feel very positive because of yesterday's condition, with respect to yesterday's condition. Same analogy here. It was occupied by a negatively charged particle, but now since it has moved out, now this place has become a more positive. Okay, so it's a hole or a vacant place or a vacancy. The terminology technically we call it as hole, so it's right to call it as hole. That means it's a place for next electron to come and sit. So what happens? This is positively charged particle. Here there is negatively charged particle. This will attract the electron towards right. So the second electron will move and occupy the vacant position. Because of this movement, the third place is now become vacant. Here again it is now positively charged. the next electron will try to occupy that position. Because of that, the positively charged hole starts moving towards left, towards left, towards left, towards left, towards left, isn't it? So this positively charged hole movement direction is considered as the direction of the current earlier. That is why in circuits, I told you, we will revisit this circuit. You see, this is the symbol of the battery. This is positive, this is negative. The positive side, from positive side, the current is flowing through the bulb. This is symbol of a bulb, and current is flowing through an ammeter. It's connected in series, and it goes through a switch. It goes to the negative side of the terminal. So the current flows from positive side to the negative side, is the direction of current for all circuit analysis. Okay. Even though we know electrons are flowing and electrons are responsible for current, electron is moving from negative to positive. But whenever we are asked to mark the direction of the current, it is always from positive to negative. It is very important to understand. I hope I have made it clear. If it is not clear, please come back. We will redo this course again. Now, what is current we have seen? It's a flow of negatively charged particles, electrons, continuous flow of electrons in a circuit is called current. How current is expressed? Current is expressed by the amount of charge flowing through a particular area in unit time. In other words, it is the rate of flow of electric charges. How do we measure? If a net charge of Q flows across the cross section of a conductor in time t, then the current through the cross section is given by I is equal to Q by T. The electric current is measured in a unit called ampere, A, capital A. It is named after the French scientist Henri Marie Ampere, who lived between 1975 and 1836. 1 ampere is constituted by the flow of 1 coulomb of charge per second. If the current measurements are done, if the quantity of the current is small, then we can use milliampere or microampere. In a shorter form, it's called milliamps and microamps. 1 milliamps is 10 power minus 3 amps. 1 microamps is 10 raised to minus 6 amps or amperes. Now, how do we measure current? To measure current, we use an instrument called ammeter. Ammeter is always connected in series in a circuit in order to measure the current. Why we have to connect ammeter only in series? Why not in parallel? Because it is necessary. Only objects connected in series experience the same amount of current. How do we understand that? We have a battery. Current is flowing through this bulb, is flowing through the switch and going back to the negative terminal. This is an ammeter. This is an ammeter. Is now connected in series. Okay, suppose if it is not connected in series, let's say I am connecting across the bulb. Okay, this is if I connect ammeter like this, then ammeter will have small amount of resistance. Bulb will have little extra resistance, not little, more resistance. So whatever current comes through that, some current will go through here, the remaining current will go through here. Okay, let's call this as I1, let's call this as I2. The I1 plus I2 will be the total I, the current I, total I that's coming. But when you want to measure total I current, you have to connect it in series like this only. then only the whole amount of current that is coming through the conductor will flow through the ammeter and you will be able to measure properly. If you connect it in parallel configuration, in one branch some amount of current will already escape and go, which you cannot measure. So you should not connect ammeter in parallel, you should connect it in series only. So ammeters are connected in series. Now an example problem. A current of 0.5 amps is drawn by a filament of an electric bulb for 10 minutes. Find the amount of electric charge that flows through the circuit. So very simple. We have learned only one equation. I is equal to Q by T. Okay. So current is Q divided by T. And what is asked in the question is Q, the amount of electric charge. Q is current times time. Current is given as 0.5 amps. That's in Paka unit. No need to change any unit conversion. T is given time, duration is 10 minutes. The SI unit is second. So convert the minutes into second. 10 minutes is 600 seconds. So 600 seconds into 0.5 amps is 300 coulomb, 300 C. So Q is equal to I into T. It's not it. It's I is current, T is small t is time. I into T. So 0.5 into A. 0.5 amps into 600 seconds, it is 300 coulombs. So that will be the answer for this particular question. Thank you. Hope you will be able to understand what is being covered. If there are any feedback, feel free to give us.